Shubham, happy morning friends. We have introduced the idea of potential. Why potential? What is the potential? Now today's session we'll do some important derivations. Right. In the case of electric field, we did some cases like electric field due to point charge, field due to dipole, and field due to distribution of charges and all. Right. Same case here also we now do the potential due to different configurations of charges. To begin with, the simplest of the case is potential due to point charge. We do some sort of simple derivation. Again, as I have told you, derivation whenever you are doing, the first line is very, very important. What is that first line? If you understand, small change in the second line change will give you the third line, and that is what is our final answer. Now here see a situation. Now here I will show an electric field first, right? Because yesterday we have two potential, two types, potential at a point or potential difference between 2 points. This is what we have explained. Therefore first we begin with the representation of an electric field, and this figure should help you in writing notes and also doing the derivation. Now here you see, first I show a point charge. This is a point charge. I show a point charge, supposing it is a positive charge. Now, due to this, we know the electric field lines are, yes, diverging lines, diverging field lines that we represent, right? So, this is what is the electric field due to a point charge. I hope you can see it. The ink is a bit faded away. Hope you can focus and see. This is an electric field such that here I call this is what is referring to reference infinity. This is what is infinity. Infinity. What is the meaning of that? See, within this boundary, this charge will affect other charges like attraction or repulsion. This is the boundary within which I said it affects other charges. Beyond that boundary, if any other charge is present, this charge cannot affect those charges. That is what is the meaning of saying infinity. In physics, whenever infinity comes, it is always contextual. Here, what is the constant? It is the distance at which the other charges have no effect due to this given charge. Now, what is our concept of potential? Do you remember? Potential energy, when we had defined a test charge moved from infinity into the field. Therefore here, now I consider a test charge. Again, test charge is always positive charge, as you know. A test charge is now moved gradually with uniform velocity into the field. These are all the things which you have already explained. So a test charge is moved from infinity into the field with uniform velocity. With uniform velocity against electrostatic repulsion, because this is a positive charge which experiences repulsion. Is it not? Now it is brought inside the electric field. Supposing against electric field it is brought, and this is some position I am writing as a point P, which is at a distance, supposing x from this given point charge. Is this given point charge? Now all these things I would like to make a simple notes. This will help you to improve your ability. I am telling you, whatever I tell you, you please take it as an inspiration and write your own notes. Now I write, consider. See how simple it is a notes making. At least at the age of 17-18, consider an electric field. Consider an electric field, yes, due to a point charge. Due to a point charge which I have taken plus q. Due to a point charge plus q. Whenever you are getting symbol, you will show them as underlined so that it will be easily visible for anybody who is looking at it. Consider electric field due to a point charge plus q. Now, another point we are making is a test charge a test charge Q0, of course it is always positive, test charge is brought, B-R-O-U-G-H, brought into the field from infinity with uniform velocity. Why uniform velocity we have already explained, with a uniform velocity. Now, in bringing the charge, we said there is electrostatic repulsion, therefore work need to be done. In bringing the charge, work is done to overcome repulsion, electrostatic repulsion, which I will write it as Coulombic repulsion. Is that okay? Coulombic repulsion, and this is what is the complete principle of our derivation. Therefore, all such cases you give a big underline for that. Say, bringing the charge, work done, overcome repulsion. These are all the essential things. And we will now calculate that work done, which will give us the required expression. Notes making is over. You see, this is what is simple ABC. Even not even high school, even an elementary class student can make such three simple statements. Right? Now I am writing. This is what is P. Supposing it is gradually brought into, and finally, of course, I name this point not P. Rather, I will call it this. Let me call it P only. Okay. P only, which is at a distance. I said not P. So let me call this. There's some reference point. I will call it like some capital R. And here is the point P at which we are interested to find the potential. And this charge, if this is what is the point O I consider. Now here I am writing OP is equal to small r. And OR is equal to small x I have taken. So this is what is, along with the figure you show this. Now, two important points, right? For Q0 at a distance, small x, from the given charge Q, from given charge Q. Then what is the Coulombic force? F is equal to 1 by 4 pi epsilon naught Q0 by x square. This is what is the Coulombic force experiencing on the Q0, and that is repulsion. Right? Now I am writing for a small displacement. How much? dx against repulsion, work done is, this was our earlier, lots of time I have spent on that, right? Now I can directly write it. The work done is dw equal to f times dx. Here this dx is infinitesimally small, therefore during that displacement, the justification that capital F is constant is very much valid, it is justified. So dw is equal to f dx. Now you see, this is what is 3-line statement, and now I will make use of this one, where the derivation actually starts. Now this is a simple notes that you can make with for yourself. Now, let me show those 3 to 4 simple simplification part. Already we have given expression for f, we will substitute it and one simple line for our final answer. Right. Therefore now I am writing this dw is equal to, yes, this is 1 by 4 pi epsilon naught, all are constants, and of course q naught is also constant. This is integral 1 by x square dx. Is it not? This is 1 by x square dx. And of course remember, this is a repulsive force, and this dw is also clearly writing this is minus f dx. Why minus f dx? This is fs cos theta is there, against the force, therefore it is minus f dx is there. So I will also here use that negative sign, yes. And this is integral 1 by x square. Now I am writing the total work done, the last line, the total work done in bringing the charge from infinite distance. See, remember, where did we begin the displacement? From infinity. Now we are taking to the point P where we are finding the potential. So the work done in bringing the charge from infinite distance to a distance small r from given charge. That is what is the total work done is integral, we write it as a dw. This integration is nothing but continuous summation. All those small displacements and those work done in those for those given small displacements added, the total work done, mathematically we call it as, this is nothing but summation only. The symbol is also s only, but that s is stretched by. This is called integral operation, which your mathematics second PU you will enjoy a lot about this calculus part. Integral dw from infinity to r. This is called initial, that is lower limit, and this is what is called as upper limit from infinity to r. So this is comes rise to, this is integral 1 by x square dx, and the answer for that is minus 1 by x. So minus 1 by x will be the answer. Therefore here I will write it as q naught upon 4 pi epsilon naught. This is 1 by x square dx, right? That integral, so there is no integral here, I am sorry. Integral is only here. Yes, 1 by x square dx there, I am sorry. So that, okay, let me show this. And this is what is integral 1 by x square dx. 1 by x squared dx. So our final answer in our next immediate step. So what is the derivation part? First you have taken this force F is equal to 1 by 4 pi epsilon naught, the Coulombic force. Then you have said dw is equal to f dx. That f dx, when you have taken, and here you have taken dw over an integral. So it was only 3-line derivation. Is it not? Writing f dw then integration. This 1 by x square, as I have told you, it is minus of 1 by x. Therefore, already this negative sign was there. Therefore, now I am writing this v is equal to negative 1 by x square is minus 1 by x. Therefore, it will be positive term. Therefore, I am writing it as, w is equal to q naught by 4 pi epsilon naught 1 by x, and this is from infinity to r, and this is called substitution of limits. Wherever you find that x, first you substitute the upper limit and then lower limit. So this is how we do the last step. Alright. So now this w is equal to q naught by 4 pi epsilon naught, or 4 pi epsilon naught, this will be 1 by r, because how you get it? 1 by r minus 1 by infinity, that 1 by infinity term we will make it as 0. Therefore now w is q naught by 4 pi epsilon naught r. Now use our definition, we got it. What is the definition of potential? It is work done per unit test charge we have taken. Therefore now we are writing by definition V is equal to W by Q naught, right? W by Q naught. Therefore here this Q naught term will vanish. Therefore, the final answer is V is equal to 1 upon 4 pi epsilon naught. 1 upon 4 pi epsilon naught. This will be Q by R Z. Now we have to discuss more about this result. I will use my next board. You wait for that. Derivation part is over. Potential due to point charge V is equal to 1 by 4 pi epsilon naught times this is Q by R. Now let us see some details regarding this expression. This is how an expression in physics is a different from a formula in mathematics. Because in each and every, any expression which we call a formula in physics is either a definition, is either a law or a principle, a concept as a whole it is. Therefore now when you look at this expression V equal to what is that? Potential due to point charge capital Q at a distance R is given by 1 by 4 pi epsilon naught Q by R, right? Q the given charge and R is the distance from this given charge, and the potential at that point is this expression. And of course, as usual, 1 by 4 pi epsilon naught I have taken as K, 9 into 10 raised to 9 for our numerical substitutions. Now here, as we have introduced the potential as a work analog, a scalar, therefore no question of any direction here. So potential is a scalar, but now what about potential positive charge and potential negative charge? So to begin with, let us say when we consider potential is positive due to positive charge and negative due to negative charge. This is the most important point. See, once you have got the derivation, you got the 5 marks answer for that. Later what work you do is very essential. This is not done by most of the students. I said 98% they don't do this work. Whoever does this work, they will find that advantage and the happiness and the healthy at the right time of your PU life. Here, when we say electric field example, we have taken always vectors. Therefore, whenever there is a system of charges, what was the idea? Idea is that write the individual vectors and take the vector sum. And hence the positive sign or negative sign in specific given to the charge, never carried into the substitutions, numerical substitutions or whatever that. Whenever negative charge is given, that negative sign is not carried into the simplifications. Remember, potential examples. In all potential examples, positive charge, negative charge makes all the difference. Therefore, that charge, that sign given to the charge, positive or negative, to be carried into the simplification, the calculations. Should not forget that. Next one. When we have given this is for due to a single point charge, right? Positive, negative potentials. Now here, what is meant by positive potential and negative potential means latter part we will make use it as higher potential and lower potential. Higher potential, lower potential. This positive potential means higher potential. Negative potential means lower potential. That's the point. And one more important point I will just mention. If for potential at a point, yes, due to a system of charges. When I said, it can be a simplest system of 2 charges and then any number of charges or even distribution of charges as well. Therefore, potential at a point due to system of charges is, supposing I show here, suppose some charge Q1, another charge Q2, some another charge Q3. These are the 3 charges. They can have positive sign or negative sign, and that is important in the case of both field and also potential, because in the case of field, to write the vector, it's important. In the case of potential, substitution is important for that positive or negative sign. So these are the 3 charges. Supposing I said this is a positive charge and this is a positive charge and this is a negative one. Now this is some point P, this is some point P, which is at a distance. I am writing this as R1. This distance is what is R2 and this distance is what is R3 distance. Maybe symmetry, asymmetry, equal, unequal, all forget about this. Now I call this point as P, therefore potential at P is equal to, I said V at P is equal to V due to Q1 plus V due to Q2 plus V due to Q3, such that when you are using these positive negative signs, and that is why I am showing you the next expression also. Then we will write what is KQ1, this is Q1, distance is R1, therefore I will write it as KQ1 by R1. This is KQ2 by R2, both are positive charges, therefore positive potential, whereas this one I will write it as minus KQ3 by R3. KQ by expression that I have used, therefore this becomes potential at point P. And therefore, for any group of charges, if we are writing it as a generalization, V is equal to, this is sigma Vi. Sigma means summation, the algebraic summation. In fact, this is what is Vi. I is equal to 1 to n, algebraic addition. In the case of field, we said vector addition. Here, potential at a point due to system of charges, this expression you write it in English as well. That is, it is equal to algebraic sum of the individual potential caused by different charges. Shall I repeat that in English? This one means that potential at a point due to system of charges is equal to algebraic sum of the individual potentials produced by different charges at that point. So that will be the simplest case. So here again we will get 2 charges, 3 charges, 4 charges, positive potentials, negative potentials, yes, even 0 potentials and whatnot. So many things they will follow. Now, so this is potential due to point charge, and one important point I would like to remind you that when you have said the field due to point charge, it was KQ by R square was there. Now please see here KQ by R only, because some students at in examination always like they complain about some things and this kind of ordinary language. Oh, forgotten, I have taken R square. See, don't have any such thing. Your practice should be so clear that it is KQ by R only, not R square. So potential due to point charge, right? Now let me take up other case. The another case is potential due to dipole.